In a previous video, I was talking about system calls and how nearly every programming language calls system calls via libc. Libc is the shared library that wraps all the system calls on Linux. It wraps them in C functions, and the reason for this is that because that's the paved road. That's how you are supposed to do this. Imagine if they change the number for a system call. So on one Linux version, it's the write system call is numbered 1. There is a new version and it is now 5. Well, that doesn't happen. But for example, when we have different system call numbers for 32 bits and 64 bits CPUs. I'm talking about on the x86. So if you call system calls via libc, then they can make these kind of breaking changes. If you call them manually, which I will show in this video, then you expose yourself to these problems. But still, let's revisit first a simple hello world in C. Let's quickly write it. stdlib stdlib.io. Sorry about my voice. And let's call printf. So this is the whole program. I am again using a very simple makefile. Let me show it quickly, but this is for single file compilation for multiple languages. I don't really want to talk about this. That's not the point of this video. So what did I do? So let's trace what hello does. So we saw that this is in a previous video. We saw that this is the meat of the program. Our printf turned into a write system call, and this is here we can see here these bytes, and the new line is what is the output of the program itself. The rest is the trace output. Yeah, but we have a bunch of other stuff here which we didn't write. We got that from GCC when we compiled it and the linker. I would like to call out two things immediately. One of them is the libc library, and the other one is the LD, which is the dynamic loader. If you look at what kind of dynamic library is our simple hello world uses, when we compile it from C, then we can see three things. So we see the dynamic the dynamic linker? No, maybe dynamic linker, that's how it is called. We see the libc, and we see something called VDSO, and for these two we can see where they are located. The exec files. For this one we don't see anything, but let's quickly find out what is the VDSO, just to not leave anything out. So we can search in the main pages with this option, and there is a man page, of course, for this. Now this is not a real file. This is a virtual dynamic shared object. And if you read this makefile, it says that basically the kernel can inject this dynamic library into your process during when it loads the program. I think you have to do some extra stuff for it, so you don't always get it. I think you have to ask the linker to inject something to it to get this from the kernel. Anyway, this is for speeding up some system calls that are very often called. I think that's interesting. So we have a vague idea about all three. what they are doing. So this is the dynamic linker, this is the libc. And now, can we get rid of these things? That's my point. So how big is the file? So it's 19K. It's not big, but there are a bunch of stuff there. We can look at the just to show the toolbox what we have. So nm is about listing symbols in a from object files. So we can call nm on the hello binary. At least it fits in one page. That's always good. And we can see the main function here, which we wrote. We see the puts. So our printf actually turned into a puts C function in the libc. It's undefined here because it's not in this binary. It's in the shared library, in the libc shared library. I will go back to this, but let's look at first the readelf. So another thing to the toolbox. Readelf, the object files on Linux, and the binary, the shared object files, the static libraries, the runnable programs are all in a format called elf. And readelf is about reading, bit about readings. Like headers and various sections from those binaries. Readelf -h means give me the header. Please read the header for me. So this is the elf header for the hello binary that we created. We see that it's an elf 64 format because I'm on a 64-bit CPU. This is what I was looking for. Entry point address. So when the kernel loaded the program, probably through execv system call, it does a bunch of stuff for you. It loads up it maps the data segment to the processor's virtual memory. The text segment in the binary is the one that contains runnable code, and a bunch of other stuff. And in that, when everything is done, it will hand over to when the kernel is done, it will hand over the user process, the newly created user process for this program, the control, and this will be the address in the binary where it will start. That will be the first instruction that it will check. So if you check again the symbols, so 1060, let's check that should be the main, right? Well, no, the main has a different address. So it is actually the start. This will be the main entry point for a Hello World program. The start is I think this is coming from the linker. So this is the default linker, the linker entry point. This is injected into your binary during the linking process. And this is this is injected, and it sets up a few things for you. Like one of them is the arguments to the function, arguments to the program, and also the environment variables. And I think it does other things. Eventually, it will call libc start main, and libc start main will call main. So a lot of things are happening before your code will be called. And yeah, you can see a bunch of other stuff here. Okay. Okay, let's move on. So we want to get rid of all of these. We want a very, very thin library that just calls write and nothing else. In order to do that, we have to go to assembly. I will use the net-wide assembler Nasm here, because that's the, I think the, well, that's what I like. Let's put it that way. So let's write some assembly. It will be very short, and I will use very few things. But maybe before we get into okay, I can write a few things. So we will have an entry point, and let's call it start, just to adhere to what the linker wants. But we can actually override this, so we could call it begin, and then we can call the linker later with the entry point. So this would set an entry point which is not the start. But that's fine. Oh, by the way, this is the comment in this assembly language. So let's not do that now. Okay, so I just wanted to show that this is not some kind of magic. It's just a default value, this start label. Okay, there are two main kinds of sections in assembly. One of them is data, which is things that are in the memory, and which doesn't have runnable code. The other section is called text. Text has instructions that the CPU should run. Of course, the text section is also in the memory, but it is marked that you can mark the different parts of the memory as for example, just only readable or read-write, and also executable. So you can play with these flags. And of course, the CPU likes to have the executable part as read-only, because then it can do all kinds of optimizations. But for example, the JIT compilers like Java and JavaScript and others are actually rewriting their instructions while they are running, and kill many kinds of optimizations in the CPUs. But everything is a trade-off. Maybe I will write some assembly that rewrites itself as it is running later. That sounds interesting. Okay, let's. We will have a simple data section. We want to put the hello string here that we will write down. So let's call this message. DB is not database. It's data bytes. So basically, I'm listing bytes here, and we can put a bunch of stuff here. What this means. So we are listing bytes in order, one after another. This is obvious, an ASCII string. So as many bytes as many characters we see, and after the comma, this 10 is actually a new line. So that's it. Now we open the text section for the actual code, and this will mark we will mark the label start as the next instruction. Okay, before I write this, let's what are we doing here? So how do we know what we should put here? So let me copy paste some things here first. So when we are calling a system call, it has a convention. Let's take a step back. So I'm only talking about the x86 -64 AMD 64 kind of CPUs on Linux. This applies only to here. So it has 16 generic registers, the CPUs. Well, not really. That's the name, that's the terminology they use, but not really generic, all of them. I mean, you can read and write to all of them, but you shouldn't. I mean, they have different roles. This CPU family has lots of history, and you do assembly here. It's all about history. So when you do a system call, the convention for them, maybe I will put it here in a comment. Oh, that's not what I wanted to copy paste. So a system call, you have to put the system call number into the register called rux. That's where you put like 1 is the write system calls number. And the system call, like a function, can have arguments. You can have up to 6 arguments, and you have to put you have to send them, all of them, in a register, because you will hand over the kernel. Well, of course, you can hand over the stack on the stack as well, but that's not how it works. And the registers in order. So the first one. Let me find it. Yes, okay, I found it. So these are the numbers. These are the registers where you have to send the arguments. So the system calls first arguments goes to RDE register, the second one to RC, blah blah blah. If it has a return value, it usually has, it will be returned in a rux value. So you just send the Syscall number in the rux, and when the kernel returns with the sysret system call instruction, the return value will be in rux. On other operating system, actually, it can return also RDX, but not on Linux. So let's forget that. Okay, so I think that's enough for now, and we can write it. So we'll move 1 to rux, because that's the number of the write system call. Why is 1? Where can we find this? I think in the previous video I did not find this, actually, the mapping from system call names to the numbers. So of course we have these man pages like for the write, but you can find the write here. It's not, but because we are off the main paved road, it's we have to find it in another way. On my machine, this is Ubuntu system. It is actually here. So here are all the names of the system calls and then numbers next to it. So we can see that the write system call has the number 1. I will use later another one. Let's find it. Yeah, the exit system call has 60. Okay, let's go back to the assembly code. Okay, so the first argument is the file descriptor. We will use the file descriptor, and which is std out, which is 1. So the standard input is 0, std out is 1, std error is 2. We are doing hello world only here. So now the message, we have to send it on the second argument, the pointer to that memory address where it starts. In Nasm we can do this like this. Address of bytes. And we need another argument which will go to RDX. which will say that how many bytes we want to write, and that's 7 with the new line. Okay, and then we can call Syscall. Now this would already work and print out hello on the screen, but this is not a proper process yet because, well, system call will return, and what happens after that? It will go to the next instruction, but there is no next instruction, so it will pick whatever it finds in the memory, and that's not good. So we, in order to properly exit from a process, we have to call another system call exit. We saw that the number for the exit system call is 60. Okay, and it has one parameter, but which is the what you get back from shell. Like if it's 0, then everything was then the process was successful. If it's not 0, then there was some kind of error, and you can get it back by the. This is how you send it back to the, for example, for the shell, if in this system call. So one way to get a 0 in assembly is like this. So the first argument is RDE. We said that RDE is to 0, and then we call Syscall. Yeah, I think that will do it. Let's see. So we call to compile this. We called Nasm to create a binary. So this is the output of Nasm itself, and then we called the linker to create a program for us, a runnable program for us. So we see that it has two labels: the start label and the message for the hello string. And then we can see that we called the linker to create a program for us. What does it help? Yeah, BSS start is these are different sections. There are two basic sections in the memory. One of them is the initialized global variables. Yeah, I am not sure about the terminology. And the other one is the also global variables, but they are not. No, the BSS section is the one that is zeroed out, and you will later initialize it. And the other section are the hardwired values. And okay, that's. I'm not sure exactly what that is now. Never mind. We have, but compared to the hello world, we got a much smaller one. Let's see the elf headers. Yes, we can see the entry point address is the same as the start. Okay, let's try it. Will it work? Yes, it did. Let's S-trace it. Ah, this is lovely. So execv, I think S-trace itself called execv to run the binary, to run the program. So we got that right and an exit. Like comparing this to the output of hello, well, there is a big difference. So we successfully called system calls in the purest form, without libc. And if you check what is do we have any link to any dynamic library, and we don't have anything. So this is at first what I wanted to show. Now, of course, we don't write assembly in itself. I mean, we don't have a program usually that is only written in assembly. But how can we marry at C and assembly? Let's make the first step. So for example, we can wrap an assembly code in a C function, and we can do that in multiple ways. And I will show all of them. All of the ones I know about. So one of the ways is to let's modify it a bit. But maybe let's write new functions. Let me copy paste this one first, then we will change it. Call me ASM. So I want to turn this into functions that can be called from C. So nearly the same what libc does for us. So one thing I can do is to separate these two. So basically I want a write C function and an exit C function, and I want to create then I want to create call this from C without libc. Can I do that? So still writing C code, but without libc. That's my next goal now. Okay, so we will need a few more things here. Let me think a moment. Let's start this over. I'm sorry. Let's start this over. What? Because I exited. Because I want that comment as well. So we saw that this is the convention how we can call a system call. That the arguments go here, and the return value will be located in the rax value. I actually didn't show that it returns that in there. Okay, later I will finish my sentence here, and then we will look at the registers that it really returns that something there. So let's talk about functions. So what is a function call? So functions are nearly the same, but of course they don't have a number like the system calls, but they have arguments. They are very similar to what we have here above. So RD, RC, RDX, they are the same so far, but the fourth argument is different between the system call and the function call. And of course the rest of the arguments, I mean the function is not limited to 6 arguments. The rest of the arguments can go on the stack. What about return value? The return value is similar. Let's go to Rex, and they can also use optionally RDX. But there are a bunch of other stuff that we have to. I did not mention something important here. Okay, there are so-called clobbers. This term means in assembly that some registers can get changed during an operation, and during a system call there are two registers that will be messed up, that you can rely on them anymore. So if you want to rely on them, you have to save them maybe on the stack first, then call the system call, and then get it back from the stack again, because the system call will mess it up. What are the clobbers? I forgot now. Yeah. We have two clobbers, RCX, R11. You know what? Before we move on, let's see these in action, because these are just all theory before we see them. One way to check them is, of course, GDB. So let's call hello ASM. We want a breakpoint on start. Yeah, that's the right address. Then we call run. One of the way to get the registers, info registers, or in short RR. You can see that nearly all registers are 0 at this moment, and we can step on the instructions with next E. It's like the next instruction. Yeah, we see that we already filled out the system call here to the RAX register. We already added the file descriptor here. Let's move till we see the hello. Yeah, so this was the moment when we called, this was the instruction when we called Syscall. So now we are back. And let's take a look. Let's compare the register, which was the clubbers. The clubbers were RCX, and R11. So those two are supposed to be changed. Yes, and they changed. So but for example, R15 is the same. The system call didn't change that. So these are the clobbers. And also we see that after the system call, the RAX has 7. So from 1 to 7. This is the return value from the write system call, which means that we want to write out 7 bytes, and it wrote out 7 bytes. Yeah. Yes, we want to exit. Let's go back to our call me. Okay, function calls. There are two more things here to know. So there are so-called callee saved registers. What that thing means. But first, let me copy paste it here so you can see as I am speaking. A moment. Okay. So these registers listed here must be saved. Must be saved by the function that got called. So because the caller will rely on this. If you mess it up and change the RBX register after you return with a ret system call, then not system call, the ret instruction, then everything, your program is off. Then anything can happen. This is you have to adhere to this convention. So the rest of the registers are caller saved. So if the caller who calls this function once, for example, the RAX register to be the same, it has to save it, because it's not guaranteed that that the function will keep it. In fact, it's nearly never keep it. So those are the responsibility of the caller to save the other registers if they want to use them. If they don't care, then they don't have to save it. But these registers, you have to make sure when you write a function that if you use them, then you have to save them first at the top of the function, and then for example on the stack, you can push them on the stack, and then you can pop it off from the stack to before you return. So we have to keep all of these in our heads before we write our wrappers around these. Okay, so let's create a few functions. We want it to be callable. So we don't have a start. We won't have a start label anymore, because this won't be a program. This will be a library. So let's call it like write in ASM, and another exit in ASM. So these will be the C function names in our for the wrapper functions. Okay, we don't need this anymore because we want this to be passed from C. So we will have a text section. Okay, let's write the first one, write in ESM. So we still want to keep this. So how would this look like in C? So we want the function signature to have an int for the file descriptor. Then we want a count star for the message memory, and we want a size to be called. And these will be called to the RD, RSE, and RDX registers in this order. Okay, if these things gets passed to us in RD, RSE, and RDX, why would they be passed to us in that order? Because a function call passes this in the same order, RD, RSE, and RDX. And this means this is exactly what we want, so we don't have to do a bunch of stuff here. We can delete lines. So RD arrives in the RD register because the function call and the system call is the same here. We don't have to move it, it's already there. Same here, same here. So actually it got a lot smaller. If we would have a fourth argument, then we would have a problem, because the function sends the fourth argument in RCX, and the system call expects it on the R10. So if that would be, if you would call a system call with at least 4 arguments, then we would have to do things like R10 and RCX here. But we don't care about that 4th argument. So this is how it looks like now. Okay, let's write the exit. It will be even simpler, because it just asks for an integer as the exit value of the program, which arrives in RDE, which matches or how the system call expects it. So we don't need this. And yeah, I think that will do it. Yes, this won't work, but I just wanted, so basically I wanted this one. At instruction expected 9th sorry, this is of course was a comment. Yeah, so if you look at the call me object file, what kind of symbols it has, we can see that it has only two symbols, the write and the exit, and this is not a program yet. Now we will write the C wrapper for it. We can write like int main. We don't call any include because we will only call those two functions from the assembly code. But we have to mark these as external functions. Right, in ESM, which had a, what was it, file descriptor, which is an int, char star, and an int of how many bytes. And it returns an int. Okay, we had an exit in ESM, which expects an int. And let's call this write in ASM 1 hello 7 and let's call it count to get back the return value. Oh, we are not done. Oh my god, sorry, let's go back for a moment to the assembly code. Call me ASM. These are not functions yet, because we forgot the most important one, ret. This is how we turn this into function. So, as we saw, when we call the write system call, the return value will be in racks for a system call. Return value in racks. And that's great, because the function call expects the return value for a function also in racks. So we don't have to move it to any other register. So if these two wouldn't match between the system call return value and the function return value, then we have to move here after the syscall. But we don't have to do that. But we have to call ret. So these are real functions this way. Oh my god. That was kinda super important. Okay. Call me c.c. At least I remember before I called it. So we get back the count, and let's check it. If count equals 7, then we call exit in ASM with 0. Otherwise, I will call exit in ASM 1. Okay, so we are not including anything. We are not calling any C function. Let's compile it. Moment, let me check a few things. Let's add some debug value. Some stuff, some symbols to be easily debugged. Call me C minus O. Call me C. Call me C.C. Okay. Now we have two object files. The call me.o from the assembly. This is the library, and the call me C from GCC, the C function. Now we want to link it together. Let's call it call me, and we link the call me.o and call me C.o. But call me C, because I named it call me C. Let's change this because I don't like it to be called like that. Okay. Yeah, we don't have a start function, but it defaulted to somewhere else. So let's see that when we call nm on call me. Yeah, we can see that the start is undefined, and this will be the entry point, the main. So it properly found the right entry point for it. If we don't want it to complain about it, we can set a new entry point as main. Then there are no complaints here. Yeah. Another way is that we can we can change this main to for example to start. It doesn't have to be a main. That's fine. Also, it can be anything. It can be begin. Not being. It can be like begin. Let's compile it like begin. Yes. Then we link it as like this. Yeah. Now, before we run it, let's check the elf sections, elf header at least of it. Yes, we call begin, that's the entry point. What else can we check? Let's call object dump on it, final. Yeah. Oh, I didn't say that Nasm, we are using the Intel syntax, and that's what I like to use. But the default on Linux is the AT&T syntax for assembly. It actually has a bunch of stuff here. Let's check call me. Okay, let's call it finally. Yep, worked. We can trace it, and yeah, clear. It just calls write and exit. So we've wrapped an assembly library that those are calling the two system calls, the write and the exit, in C functions, and we call them. Now I want to show another way how you are able to call assembly in C, which is via inline assembly. Let's call it hello inline. So we will include a bunch of stuff. Now we are not we will use libc, so we are abandoning that line, because we will write only only in C. So what I want to show is that you can put the assembly in C code and call system calls directly in C without libc. But the code itself for other parts, it will use libc. Just not for the write and for the exit, or just for the write. So I'm also pulling in a string because I will call stringlen on something. Okay. So we need a main function. So we'll do a similar thing as before. We'll call something like call write, so not directly printf, but our own function, and call write will be implemented with assembly inside. But call write itself is still a C function. And I want a similar interface to it as before. We could put one here as the file descriptor. So the order was file descriptor, memory, and size of the how many bytes. And but there is a better way to do it. Is that from a file you can turn this into a file descriptor via the function called file. So this is something I use libc now for. So what do I put here? std out. This is basically equals to 1. This is the same now. But this is a more portable way of doing things. For example, if I don't want to write only to the standard out later, but to a real file, I could put a file star here later. So this I'm thinking ahead of the future here. And let's have a slightly easier interface. So I will not send the bytes, how many bytes, but the function will calculate it inside. Okay, and I will do the same here. If count equals 7, then I will not implement the exit now. We already saw that. We won't learn more from that. Okay, let's now implement the meat of it, which is the call write. So file descriptor and message. I'm copy pasting this here. I didn't keep this in my head. So we will get the length of the message. That's why we included the string here, string header here. So we can pass it in to the assembly, and then we will use this as a return value. We did not initialize it. We will fill this out in the inline assembly. Now the meat. Let's talk about the meat. So GNU, the GCC has an extension to C, which is the syntax called something like, looks something like this. Now I don't want to talk a lot about this. I don't want to go very deep into this. It's kind of messy. So here you put instructions like move, racks, whatever. It's supposed to support Intel syntax as well, but I could not make it work. So actually I had to use AT&T syntax in the end, which is a bit uglier and more verbose. The first part here is kind of outputs, inputs, and clobbers. Clobbers like we saw it's the same terminology that we saw in the system call. So the system call changes a few things, and this is how we can alert the compiler that we don't change only things that are listed here or here or here, but we change things that are not listed there. So we warn the compiler for this, and then it cannot rely on it. Let me show an example. So for example, this is a valid code that I will show. This is not a register, it is just a word called memory. This line actually is a memory barrier. So how to read this? We are not calling any assembly, we are not having any input, output, input, but we have one clobber, which is memory. This signals to the compiler that everything before here and after this line things should not be reordered. Like here is someone reads something from memory, and here it also reads something from the same thing from memory. So above this line and above this line, then the compiler will see that, oh, we already read this, and without this line it will optimize the second one away. But if you have this memory barrier here, then this would mean that the compiler and also the CPU will call it, call the read operation again, because it could have changed. Yeah, I could have explained this better, but I don't have a better words for this now. So let's implement the meat. I will copy paste the whole thing here first, and I will rather, instead of writing it out, I will rather talk about it. So, as I said, the syntax is a bit ugly. I just wanted to, with this, I wanted to show that it is possible to marry assembly and C inside the same file, and you don't have to call Nasm to compile a separate assembly library, but you can merge these only with the using the C library. AT&T syntax, so the order is different and it's a bit more verbose. The $1 means it's a literal one that we move into the RAX register, so it's similar. EDE, yeah. So these registers has lots of history here. These registers are 64 bits, usually, like the RAX, 64 bits, and what it in the 32-bit processors, it had only 32 bits, and those old registers has a different name. Same for the other first eight registers. And before that, the CPU was 16 bits long, and those registers are still there. You can refer to only those parts of the big RAX register, and those also have a different name. And these are, after the move, it means that what is the exact size of the registers that you are touching, or the full register, or only half the register, or 1/4 of the register. That's how you can read it. But otherwise, this is the same. Let's maybe take a look at the output and input. So here we are listing the output, which is the count. This is the same reference to that variable, and the system and this assembly will fill it out. And this is how we can add input to the assembly. The FD, we are directly referring to these arguments. Message here, and the length here. The R means that please store it in a register. Please store it in a register. Same here. And then we can refer to these by numbers. First, second, third. Why first? Because actually this is the 0th one. So if we would have no output, then it would be 0, 1, and 2. What does... Damn, I forgot what is the A. No, this is the A refers to the RAX register. Okay, thank God. So it took me a while to actually create this example. It is, I will send a link where it is documented. It didn't help me a lot. So as I said, Intel syntax should also work. It didn't work for me. I couldn't make it work. I have examples that compiles, but I just didn't work for me. So what else this section does? So obviously it will insert this somewhere into the function, into the middle of the compiled function, but it will also generate code for these parts, for the output after the assembly part, and for the inputs before this section. So it helps us it generates these wrappers for us. That's the value of this inline assembly. Yeah, I think let's compile it. Let's see. Can we compile it at all? Okay. Maybe I have the problem with the maybe. This is just GCC. we actually have to use the GNU, so we can't use like this, because this is a GNU extension. What was the name? It was not Hello Inline. Hello Inline dot hello Inline. Let's see. Yes, compile. And it worked. So it called write correctly. It has also start and main, because we are using libc here, so same dance that we had before, but we have the call write here. What else can reader will not show anything interesting. So by the way, make didn't work because this library that we wrote in assembly and the C program that called that library is not supported by this make. This make file is just for single files. What did I forget? So why I was talking about where is it? Nope, that's not the good one. So what I put here into the comments. So the how we call the system calls, what registers you put them, what is the return value, globbers, all of these things are where are they coming from? How can you know? Well, of course, you know, there's always man pages. Probably you can find it somewhere there, but that's not all. You can these are coming from so-called Linux ABI. Let me show the latest document for the Linux ABI. Let me put myself a little smaller. I will put a link to below the video how you can find this. So this is a 150-page long document. This is the Linux ABI, the application binary interface. This lists everything, how all the conventions, all the binary format, how a program looks like, how the process initializes, shared libraries, ELF, and also the conventions. So if you want to implement it in any language or any way, basically you can write an ELF binary by hand just by going through this. And let's see the calling conventions. So it's very late in the document. 32 bits and 64 bits are different. They have different registers, so it must be different. And here you can see that how the functions are called, what kind of registers they are using, and what kind of registers the kernel uses. So these are the system calls. We can see that the fourth one is different. RCX for the functions, R10 for the system calls. The system calls done via the Syscall instruction. This is only true for the 64-bit CPUs. Earlier it was an interrupt on 32 bits processors. Maybe there was a different way as well. Never mind. Then here is the description of the globbers I mentioned, that those two registers will be not can be changed, and you can't rely on them. Those are the globbers. Yeah, the number of Syscall has to be passed on RAX. So everything I was talking about, every convention we relied on is listed in this document, and lots of other stuff that I did not talk about. Okay, I think it's time to time to wrap it up. Okay, so what we saw. So I showed how you can, I showed you the tiniest program you can make that calls a system call on Linux without going through libc. I also showed briefly some tools from the toolbox, like listing symbols with enum, reading the elf header with readelf. Yeah, I showed object dump, but that was really brief. I didn't talk about it. Yeah, we saw also that with the linker that we can set a different entry point with this. And I showed some really tiny assembly code, both in AT&T syntax and Intel syntax. I really think that you should always use Intel syntax, but that's just my opinion. I'm actually not an expert in assembly in any way. Yes, I think I will stop here. I have several ideas what to talk about next, but during this recording, I got the motivation to write an ELF file, ELF binary by hand. I don't know what kind of video I can make of it, but that sounds really interesting. Thanks for listening. Bye bye.